Hello, and welcome to this new session of my course, Animated Multimedia Application Design, where we will explore the multisensory modalities beyond vision.
Sound is a vibration produced by a source and perceived by the human ear as an auditory sensation. Sound modeling is based on a biological process. A sound source emits vibrations which are captured by a microphone and converted into waves. These waves are then sampled and quantized to assign digital codes to each sample. Digital representation of sound involves capturing and encoding audio signals in numerical form. To accurately reproduce sound, the sampling rate must be at least twice the highest frequency present in the signal, according to the Nyquist theorem. Since the human hearing range extends from 20 to 20,000 Hz, standard audio systems typically use a sampling rate of around 40,000 Hz, commonly standardized as 44.1 kHz. The bit depth, on the other hand, determines the number of bits used to encode each sampled value, directly influencing the precision and dynamic range of the recorded sound.
To demonstrate the impact of bit depth on sound quality, here is a recording with an 8-bit depth. And now, the same recording with a 16-bit depth. Sound serves multiple purposes in multimedia applications. It provides direct information, such as speech, dialogue, or music, which conveys explicit meaning and content. Additionally, it offers contextual cues, including spatial positioning, distance, ambiance, and environmental sounds that help create a sense of space, realism, and emotional atmosphere. Various tools are used in the creation and manipulation of sound. These include recording and playback systems that capture and reproduce audio, synthesis and transformation tools that generate or modify sounds, and sound effects tools that enhance realism or artistic expression. Additionally, editing and montage processes allow precise arrangement and refinement of audio elements, while mixing and mastering ensure balance, clarity, and professional sound quality in the final output. In implementation, sound is not as lightweight as text in terms of storage and processing requirements. However, it remains one of the most widely used communication channels due to its expressive and immersive nature. Thanks to modern compression techniques such as MP3 and AAC, along with efficient encoding methods, the storage and transmission of sound have become relatively manageable without significant loss of quality. For the haptic dimension, things are a bit more complex. Unlike sound or image, the haptic modality is not as straightforward to define, as it involves the entire body in the perception process rather than a single sensory organ. It encompasses multiple expressions, including touch and proprioception, which covers posture, orientation, and movement. Perception in this context results from the brain's interpretation of audiovisual information combined with somatic stimuli from the body, creating a unified sensory experience. Olfaction, sense of smell, refers to the process by which humans detect and perceive odors. The biological mechanism of smell begins with olfactory receptor neurons, located in the olfactory epithelium, a yellowish lining inside the nasal cavity. When chemical stimuli, airborne molecules, enter the nose, they bind to these receptors, generating signals that are transmitted to the olfactory bulb, where they are processed and relayed to the brain for interpretation. Gustation is the process through which humans perceive flavors. The biological mechanism of taste involves taste buds, which are clusters of receptor cells located on the tongue and the oral mucous membranes. When dissolved molecules from food or drink come into contact with these receptors, signals are sent via the gustatory nerves to the brain,
resulting in taste recognition. Utility of olfaction. Though rarely implemented in multimedia systems, olfactory feedback can significantly enhance the sense of presence, enrich storytelling through memory and emotion, and simulate environmental conditions for immersive experiences. Utility of gustation. The gustatory modality is even less explored, yet it holds potential in culinary simulations, gastronomy training, medical rehabilitation, and experimental entertainment aimed at expanding sensory storytelling. Humans can perceive 5 universally recognized basic tastes: sweet, associated with sugars; sour, linked to acids and pH balance; salty, related to mineral salts and electrolyte balance; bitter, often signaling potentially toxic substances; and umami, a savory flavor derived from amino acids like glutamate. In terms of smell, humans can discriminate around 10,000 distinct odors, and recent research suggests that the olfactory system may differentiate up to 1 trillion unique olfactory stimuli. This extraordinary sensitivity highlights the complexity and richness of our perceptual abilities across sensory dimensions. Challenges and limitations. Perceptual and physical constraints. There is no precise scale or defined range of perception for smell and taste, making it difficult to reproduce or control odors accurately. The chemical synthesis and storage of scents are complex, requiring non-toxic, stable compounds. Ergonomic constraints. Artificial scents can create contradictions or interferences with visual and auditory stimuli. Additionally, delivery mechanisms for taste and smell must be precisely controlled and localized, for example, within the tongue or oral cavity without causing discomfort. Cognitive constraints. The persistence of smells poses a challenge, as odors diffuse slowly and are difficult to remove quickly, complicating real-time synchronization. Aligning olfactory feedback with visual and auditory cues can lead to perceptual mismatches or contradictions. Advanced tools and research in olfactory simulation. Recent innovations include olfactory displays, devices that emit controlled scents, and micro-diffusers designed for targeted scent release. In addition, wearable olfactory devices are being integrated into virtual reality systems, and experimental platforms are emerging to study cross-modal interaction between smell, vision, and sound. Advanced tools and research in gustatory simulation. In the gustatory field, research is advancing toward electronic tongues capable of detecting and simulating taste profiles. Techniques such as electrostimulation of taste buds are being explored to reproduce taste sensations digitally. Furthermore, wearable gustatory devices for VR and AR environments are opening new possibilities for immersive multisensory experiences.